This video marks the first day of Chapter 5, which is a topic in physics called electrostatics. Just so you have a feeling for where we're going, the second half of Physics 12 is all about electricity, and it's 3 chapters. The first one is electrostatics. We're going to look at what happens when charges are sitting near each other and how they can push and pull on each other and how it would be sometimes a lot of work to move them around. The chapter after that is one that you're familiar with from grade 11. It's electric circuits. And then the final chapter is electricity and magnetism, looking at how you can use electricity to make magnetism and the reverse, how you can use magnets and magnetic fields to make electricity. But this one is electrostatics. It's all about charges. And so we're going to jump right in. And you can be filling out your little note template booklet here. Save you a lot of time if you've printed that booklet off, and then you can just fill in the blanks essentially. The first main topic we're going to look at is Coulomb's law. It's named after Coulomb, and it's a description mathematically of the electrostatic force between two charges when they're near each other. So here are some things that you probably already know just from your previous knowledge in physics. If you have two positive charges, like two protons, they're going to repel each other. And if you have two electrons, if they're the same but negative, then they're going to repel each other as well. But if they're unlike, if you have maybe a proton and an electron, or a positive and a negative charge in general, then you're going to find that they attract. Now I'm going to use the phrase "use your head," not in a disrespectful way, but in a sense where we're not going to use any math to try to incorporate those ideas, not at this level. We're just going to use our head to think about direction every time, and we'll use the math to figure out the size of the force. So there are a lot of possibilities here in terms of the charges. They could both be positive, both negative, or one of each. I'm just going to draw this as two positives for now, some distance r apart. And these are what we call point charges, so they don't really have any thickness to themselves. So whether you're measuring from edge to edge or center to center, you really can't tell the difference at the level that we're going to be working at. So it's not like with planets where you have to be really careful about measuring to the inside. So those are two positives, and we know that those two positives are going to repel each other. So I'm just going to draw those repulsive forces in. And for the lack of any better way of talking about them, I'm going to call them F12, the force that happens when charges 1 and 2 see each other. And we're going to try to find out how big that force is. That's what Coulomb's law is all about. And here it is. It's very, very similar to gravity. For gravity, it would have been a constant that was a large capital G. Here it's a lowercase k. Actually, what's ironic is this small lowercase k is actually a much, much bigger number than the value we had for capital G in gravity. And then instead of the two masses that we would have had for gravity, we're going to be looking at the two charge values, which we're going to denote with the letter Q. That's going to talk about how big those charges are. It's actually measured in coulombs. And then just like with gravity, it's an inverse square law. So we'll divide by the distance between those charges squared. Okay, so it's going to abide by all of those square law relationships that we know. So here's just a little legend of all of the things that you'll find in Coulomb's law. F is, of course, the force. That's what this equation is all about, calculating that repulsive force in this case. Sometimes it's attractive, but here it's repulsive. It's measured in newtons. That force is going to be a vector, so it has size and direction. And that equation is great for the size, but not so good for the direction. So for the direction, you're going to have to actually just use your noggin, look at it and go, hey, going to be repulsive because it's two positives. The Q's are going to be the charge values measured in coulombs, and the abbreviation for a coulomb is a capital C. R is the distance. It does have to be in meters, so many times in the notes I'm going to try to trick you and put it in centimeters, and we'll have to always go, oh wait, got to shift that over to meters. And K is this constant that we'll use all chapter long for electrostatics. It's 9 times 10 to the 9. You might want to even just put that into your graphing calculator's memory under K, just 9E9, and then store it in K. You don't have to worry about the units too much. They're kind of messy looking, but I promise you if you measure the R in meters and measure the charge in coulombs, everything will work out to be in newtons in the end, and that's what we want. So there's the relationship. There's Coulomb's law, K, Q, Q, all divided by R squared. Now before we dive into the rest of the notes that are on your template, let's just look at this inverse square law for a minute and talk about how things will change if you change the R. Because it is an inverse square law, if you were to make the R larger, the distance between the charges, if you made it grow, then a bigger value for R will give you a smaller force, but actually a much smaller force. So if you made the R, say 7 times bigger, if you didn't change the q's but just made the r 7 times bigger, then the force would go down because you made the r bigger, but not by 7. It would go down by 49. And you can play the game in reverse. If you made the r 3 times smaller, then the force will grow by a factor of 9. So I'm always squaring the factor that people are changing the r by. Somebody says, oh, I made the r 5 times bigger. Oh, then the force went down by 25. You can play the game backwards. If somebody says, oh, well, the force got smaller by a factor of 81. Oh, well, then you must have made the r bigger, and you didn't do it by a factor of 81. You must have done it by 9. And so there's always a square root relationship when you're trying to take changes in force that you know and figure out what happened to the r. Okay, in this chapter we're going to find that coulombs are very large charges, and we will rarely play with full coulombs of charge. You're going to quite often see millicoulombs. That's what the little m is. This is just right off your formula sheet. It's on the back. So milli is 10 to the negative 3. Micro, that Greek letter, that mu letter, is 10 to the negative 6, and we will have a lot of microcoulombs. And then there are nanocoulombs, 10 to the negative 9, and picocoulombs are very common as well, 10 to the negative 12. Now you can get smaller charges, but at some point there is a limit on how small they can be. The smallest possible charges that you will ever measure in nature are what we call the elementary charge. And there's a positive elementary charge and a negative elementary charge. And those are the charges on a proton and an electron. So a proton has a charge of 1 positive elementary charge, and its value is incredibly tiny. It's smaller than a picocoulomb. It's 1.6 times 10 to the negative 19 coulombs. An electron, even though its mass is a lot smaller than a proton, its charge is the same size, but negative. So it's an elementary charge, but negative in polarity, as we would say, negative 1.6 times 10 to the negative 19 coulombs. So if you ever need to know the charge on a proton or an electron, you can just simply look those up. All right, we're just going to try a couple of examples out, and then we'll be done this lesson for the day. First one here says, can you find the force on Q2? Just Q2. I don't know why they don't want to worry about Q1, but they're like, just Q2. What's happening to it? Well, I need to find size and direction for the force acting on this thing. For direction, I can just use my head. I can look at it and go, whoa, there's a positive and a negative. Those two charges are going to attract. And even though one is bigger than the other, they will attract with the same size force. So I've got half the story done. I know it's an attractive force pulling Q2 back to the left. Now, for size, I'm going to go and just use Coulomb's law. But be careful. You've got centimeters in there, which will have to get changed, and you've got microcoulombs in there, so we have to watch out for those. So here goes Coulomb's law. It's kind of like doing a gravity force calculation, but there's just a different constant for this chapter. And then 24, again, microcoulombs, 10 to the negative 6. 38 microcoulombs, and I deliberately did not put the minus sign in. At this level of physics, the math does a poor job of trying to figure out direction. Just don't even bother putting it in, and that's why I use the phrase, just use your head, just think about it. But I do change that distance to meters, 0.17, and it does have to get squared. And then if you try throwing that into your calculator, you'll see it's 284 newtons of attractive force. And since they're saying, oh, just worry about Q2, then I guess its attractive force is to the left. Okay, just a few more. This one here, find the force on a couple of protons 40 centimeters apart. Okay, so sometimes people are going to give you the size of the charges in words instead of numbers. So when they say protons, I know I can go and look up the size of those charge values. So it's going to be a repulsive force because they're both positive. And so I can already start drawing that in, definitely pushing away from each other. And now I go to the formula sheet to dig up that elementary charge value. And for the value for K if you've forgotten it. So 9 times 10 to the 9 is the K we'll use every time. And then 1.6, 10 to the negative 19. That's how many coulombs there are on every single electron. That happens twice because there are 2 protons in there, right? Sorry, I said electron, but it's the charge on either one, a proton or an electron. But they do occur twice, so I have to put the Q in for one proton and then again for the other proton. And divide it by the distance in meters, getting squared. And then you throw that into your calculator. It's negative, oh, I shouldn't say left in here, because this one doesn't talk about one specific one. Let me fix that right on the fly. So this is repulsive, because those protons are definitely going to push away from each other with 1.44, 10 to the negative 27 newtons. Now, just a little bit of trivia. If you were to check out the force of gravity between those two protons, they are massive, right? They've got some mass to them. If you did G_mm all divided by r squared and figured out the value, the size of the force of gravity, it would be incredibly tiny compared to this electric force. So when we look at these questions and we're trying to find the force they apply on each other, you do not have to worry about gravity forces. They are so many times smaller that they're just not an issue for us. The electric force is much, much more dominant than the gravity force. Okay, second to last question. Sometimes we're going to have a whole bunch of charges all on the page together. We did this with gravity as well. So this is what we could call superposition. What if there's a whole bunch of effects that are adding up? And this says, can you go and find the total force on each charge? Like this 18, how much overall force does it feel when both Q2 and Q3 attract it? Or what about Q2? How much force does it feel when Q1 attracts it and Q3 repels it? And then Q3, it's going to get attracted to Q1 but repelled by Q2. We have to do all three of these, but we're going to be efficient about it. Let's go pair by pair. When charge 1 and charge 2 see each other and they start talking to each other, you've got one positive and one negative, so they're going to attract. And for the lack of any better way of naming that, I'm going to call that force 1, 2. And we can go and find out how big that force is. We'll just use Coulomb's law. So 9 times 10 to the 9 is the K, and then I put in the two charge values. Once again, notice I'm not even bothering putting in the negative sign. I know they're attractive. I've already got that in the picture. And I have to divide by the distance squared in meters, and I find that that value is about 99 newtons on each of them. They apply that much force on each other, even though one has more charge than the other. Okay, 1 and 3. Even though 2 is standing in the way, 1 and 3, they know each other's there. They know that they're of opposite sign, or we would say of opposite polarity, so they're going to attract. And we can go and figure out how big that attraction is with Coulomb's law. So we've upscaled to 21 microcoulombs instead of 12 compared to the last calculation, but it's farther away, and that distance is so important. So we end up with less force, about 54 newtons there. Now the last pair to look at, what about 2 and 3 when they look at each other? They're both negative, so they're going to repel each other. I'm going to call that pair of forces F23, and I can use Coulomb's law again to figure out how big that value is. For both of those charges, those F23 values, when you run the values, you get 187 newtons. Now, we're not really finished this question yet, but we're very close. The question said, no, go and look at each charge one at a time. So Q1 has a couple of forces, and they're both to the right. We're going to have to go add them up. Q2, it has a couple of forces, and they're both to the left, and we're going to go and add those left forces up. And we'll be a little more careful with number 3 because it's got one force going left and the other one going off to the right. And so here's what we find, finishing this off. Q1, 99 newtons on it to the right, 54 to the right, for a grand total of 154 to the right. Same game for Q2, 99 left, 187 left, for a grand total of 287 newtons to the left. And Q3, so again, these forces are vectors. We have to use our head and be thinking about the direction. We've got a 54 left and a 187 right. So they're going to battle each other. The rights are going to win. They're a little stronger than the lefts, and so we'll have 133 newtons to the right. And that's pretty much the end of the story. The one thing that we're going to be just a little bit careful about this year, because we're doing this all online, is the next topic we would look at is what about like two-dimensional stories. So I'm going to show this to you, but I wouldn't worry too much about it for now. But here it is. Here's a two-dimensional story. In fact, it's the same numbers in the last question, an 18, a 12, and a 21, just looking back. 18, 12, and 21. I've changed the polarity of one of them, and we still have the 14 and the 11 distance as well. And people might ask, well, what's going to happen to Q2? What's the total force look like on that one? We've actually got the numbers from the previous page for what happens when an 18 microcoulomb and 12 microcoulomb charge are 14 centimeters apart. We already know that. That was back here. 18 and 12, 14 apart. That's actually going to be 99 newtons. And we even know what's going to happen when a 12 and a 21 are 11 apart. Okay, we've done that one on the previous page, right? The 12 and 21, 11 apart, that's the 187. The only thing that we don't deal with on the previous page that we have to deal with here is that two-dimensional direction issue. So force 1, 2 would be down, repulsive on charge 2. There's actually a repulsive force on Q1 as well, but I'm just too lazy to draw it in. And then 2 and 3, that would attract Q2 towards Q3. And so I need to take these two values, but I can't simply add the numbers. So you'd have to be careful if you were going to do questions like this. These are sort of optional now for doing this online. We've got 99 down and 187 to the right. And so the answer is it's just not going to be 286, right? We can't just simply add those. You would have to add them as vectors with Pythagoras and then doing some right angle trigonometry. We've done that many times, so I'm just going to draw this really quickly and say, yep, okay, it won't be 286, but instead it's 212 and 28 degrees south of east. And that marks the end of our first lesson. So it's Coulomb's law, looking at how we can find the force between two charges using that equation K, QQ, the charge values, divided by the distance, the r squared. And then for the direction, we'll just simply use our head. And that's the end of lesson number 1.